PhD in Sustainable Futures from the University of Technology, Sydney. Wahidul teaches and coordinates a core undergraduate engineering unit, Engineering for Sustainable Development at Curtin University. He has so far carried out extensive life cycle assessment and sustainability related research on Australian agricultural, alternative fuels, building and construction, manufacturing, mining, and water sectors for the Department of Climate Change, Department of Agriculture, Department of Primary Industries, Victoria's Meat and Livestock, Worley Parsons and Water Corporation, Enterprise Connects and Recon Engineering, Cedar Woods, Earth Care and Department of State Development, Cockburg Cement Limited, Waste Authority Western Australia, Woodsides Energy Group Limited, and the list goes on, goes on, goes on. So such a wide experience in designing the framework, sustainability assessment systems. So without any further delay, we'd like to hand over our platform to Associate Professor Wahidul Biswas, who will be speaking on an integrated framework to assess the sustainability potential of alternative fuels in a life cycle approach. Sir, we welcome you on board, and now the platform is for you to share your knowledge and expertise with us in enlightening us in how to develop a sustainable framework.
Okay. Thank you very much, Dr. Chela, for nicely introducing me to the audience. And I would like to express my deep gratitude to Professor Dubey to invite me to this special event and a very topical issue on decarbonization of India's transportation system. And this is indeed a great opportunity for me. So I'm going to share my PowerPoint slides. So okay, good. So everybody is able to see my slide. So it is okay?
Yes, sir.
Okay, thank you very much. So now I can move on. Okay, my today's presentation is on an integrated framework to assess the sustainability potential of alternative fuels, a life cycle approach. So life cycle can help achieve a sustainable solution. It can help in the decision-making process, and we can apply in different sectors come up with sustainability strategies which can further improve social, economic, and environmental performance of a product. It can be biofuel, hydrogen, building, water, construction, manufacturing, agriculture, whatever. So I always start, since I came from an engineering background, I always start my presentation with this powerful definition on sustainable engineering. And I like this definition. The engineering context of sustainability involves the design and management of sustainable technology, which is economically, environmentally, and socially sustainable, research into environmental and social impact and limitation, living within global limitations. We have got one Earth equivalent amount of resources. At the moment, we are consuming more than 1.8 Earth equivalent amount of resources. If we are not changing, if we are not innovating, if we are not take a drastic action, so we need 3 to 4 planets by the middle of this century, but we don't even have a one planet. So we need to apply innovative engineering design that will enable us to live within our means or within our carrying capacity. So management of resources from cradle to cradle, we need to design product in a way that it can be remanufactured, recycled, recovered. So end-of-life product can be turned into a new product if we're able to avoid sink, we can automatically avoid soak. So life cycle assessment can help us achieve a cradle to cradle design that will help achieve a circular economy, that will convert waste to resources, that will have positive economic, social, and environmental consequences. Soon after the 1992 Rio Summit, a group of engineers investigated that there were 2,500 issues, and of these, 1,700 are indirectly and 241 are directly related to engineering. So engineering play a pivotal role in achieving sustainable development. So when we assess sustainability, we need to select indicators, and indicators vary from product to product, country to country. So it can vary with countries, regions, because of socioeconomic condition, because of climatic condition, because of differences in the manufacturing process, etc. So the indicators that we will be using for milk production or assessing the sustainability of milk production, we cannot use them for iron ore production because processes are different. Also, the indicators that we will use for iron ore production in Australia, we cannot use in India because socioeconomic condition, geography, physiochemical characteristics vary across region. So indicators selection is an important part when we are doing sustainability assessment. So in the case of indicators, there are different types of indicators. That is, one is tangible indicators that we can quantify, like greenhouse gas emission per ton of iron ore production, or per kilometer vehicle travel, or in the case of intangible indicator, it is something qualitative, means that we cannot quantify, but we have got a procedure to convert this qualitative values like fair, unfair, happy, unhappy, satisfaction, dissatisfaction. All these qualitative values can be converted to quantitative values so that at the end of the day, we can integrate all triple bottom line indicators in order to determine or obtain a single score for sustainability. So these are some typical examples of indicators. So indicators needs to be determined in a way that it is not increasing the cost, it is not increasing the workload. So we need to be very smart in determining the type of indicators that will be used to assess the sustainability performance of a particular product. So having a good number of indicators doesn't mean that we are doing a good job. So we need to determine as small as a possible number of indicators so that it can represent the whole system. For example, if you look at this indicator, number of school dropouts, it is mainly relevant to mining industries. If the number of school dropout is increased, it means that the parents are leaving. Why parents are leaving? Because there are some problem in the environment or surrounding areas. So this gives an indication that something wrong happening in that particular area. So we need to use the indicators in a way that it represents the product, it represents the characteristics of the product, and it can help assess the sustainability performance of a product. Now, how do we do this? There are 4 steps. Number 1, those who are researchers, they need to do a literature review to find out what are some indicators considered by other researchers when assessing the performance of a certain product. Then the researcher has to conduct a survey, and they need to engage the people who are expert in this area to provide opinion, whether it is relevant or irrelevant. Also, there is a provision for them to provide some additional indicators in case the researcher is missing. When they're providing this consent, at the same time, they are requested to provide the ranking of these indicators. Ranking means whether it is very important, or less important, and moderately important, etc. Now, what happens that once the indicators have been selected, finally selected after this survey, and these ranking are converted to weight, because we cannot give equal weight to all indicators. So different indicators will have different weights, and this vary from country to country. Now, once we have selected the indicators pertaining to the sustainability assessment of a particular product or service, once we have estimated or determined the weight of these indicators, we need to estimate these indicators. So how do we estimate these indicators or determine these indicators? By using life cycle assessment approach. Now, in the case of life cycle assessment, there are 3 tools. Environmental life cycle assessment that will allow us to calculate environmental indicators, social life cycle assessment that will allow us to calculate social indicators, and then comes life cycle costing that will allow us to calculate economic indicators. Now, as you are aware, the life cycle assessment takes into account all stages of product life cycle, and it helps identify the problematic areas so that improvement strategies can be applied and restructure the supply chain and making a green product. Now, this life cycle assessment can help compare different products doing the same job or different versions of the same product with reduced environmental impact, social impact, and cost impact, etc. Now, this life cycle assessment can help us in green product design by identifying the hotspot, which process or which chemical in which stage causing the most impact, so that the right solution can be provided. I often say to my students that yes, what doctors cannot do, engineers can do. Engineers can turn end-of-life product to a new product through their innovative design process, so that we need to consider at the design stage so that at the end of life, we can prevent the disposal of end-of-life product to landfill and turn into a new product by disassembling, recycling, recovering, remanufacturing strategies. So life cycle assessment can help us design a product that is durable, recyclable, that can be remanufactured, that is green, and with reduced carbon footprint or environmental footprint. It can help design innovative processes, refinery processes, manufacturing processes with reduced oil, with reduced lubricant, with reduced chemicals, with more recycling strategies, etc. it can help develop policies. I always share these examples with my students and other colleagues that in 2008, I got a call from Australian Broadcasting Corporation, ABC. That time the government was phasing out the incandescent lamp. So, and that is these incandescent lamps were going to be substituted by compact fluorescent lamp. So I've been asked that, yes, that what you suggest, because some people are very skeptical because the compact fluorescent lamp has got mercury. It is very difficult to recover mercury from compact fluorescent lamp. If it is straight away goes to landfill, it can cause huge ecotoxicity or water toxicity, etc. What are you going to do? So I did not have any answer. So in 3 to 4 months, I got a chemical engineering student who completed a honors project with me. And from his LC, it was found that the amount of mercury emission that will be avoided due to replacement of incandescent lamp with a compact fluorescent lamp is significantly higher than the amount of mercury in compact fluorescent lamp. So what the government has done is okay, because it is reducing mercury emission, carbon emission, conserving energy for our future generation, and helping achieving circular economy, etc. Market strategies, so market for green product, like market for biofuel, market for hydrogen, market for green steel, etc. And supply chain management. Supply chain management means so people in the downstream, stakeholders in the downstream supply chain can pressurize the people, stakeholders in the upstream supply chain, like miner, manufacturer, processor, to improve the processes, because the stakeholders in the downstream supply chain are the main gatekeepers, and they're responsible for paying for the tax. So if the emission is reduced in the upstream mining, manufacturing, so that it can help reduce the burden of tax when they're selling this product to the customer. So, this life cycle assessment, this follow international standard organization guidelines. So it has got goal and scope, then life cycle inventory, then impact, then interpretation. Now, goal and scope, it varies from country to product, company to company. So, and they have got their own intention. So sometimes they're interested to know the carbon footprint of the production, manufacturing of a car instead of driving a car, or they're interested in the carbon footprint of milk, not the cheese, or not the. So it varies from company to company, etc. Now, in the case of scope, scope depends on the goal, and scope and goal set up the boundary. Now, boundary means that number of stages in product's life cycle that needs to be considered. Now, once we have and in order to, and we need to have a functional unit so that can help us capture all inputs and outputs that were used and emitted during the life cycle of a product. So this functional unit helps us do a mass balance, estimate or quantify the amount of inputs in the form of energy, electricity, chemical, water, material used in different processes in different stages of product life cycle. So once we know the amount of inputs and outputs, then we can convert them to emission. emissions, and different emissions causes different impacts. We can classify them. Then we can convert these emissions to impact. So now this is how we do the environmental life cycle assessment, and we quantify these values. Most of the values that we quantify for environmental life cycle assessment are tangible variables. Now, our indicators, but in the case of social life cycle assessment, we interview the people who are affected, who are directly or indirectly linked to the production, and we use a Likert scale, and the maximum point is strongly agree, highly satisfied, and another extreme is not satisfied, disagree, etc. So we need and we use this scale to get their opinion. So if it is a 5-point Likert scale, and if the maximum point is 5, and if their satisfaction level is 3, then there is a gap. What is the gap? 3 minus 5 equal to -2 is the gap. So this -2 is multiplied by the corresponding weight. As I mentioned to you, that these weights are discerned or determined by the responses given by the experts during the survey. So once we have multiplied by the gap, which is -2 or -3, by corresponding weight, we get the social impact score. So this is how we determine social impact. Now, in the case of life cycle costing, we consider the same inputs that we have considered in the environmental life cycle assessment. Only the kg, liter, kilowatt hour, gigajoule, cubic meter, all these values are translated to dollars. So that we can do the life cycle costing for the same system boundary, for the same stages, for the same inputs, etc. Now, when we do life cycle costing, we need to anticipate, because we need to anticipate that what is going to be the future cost. But although it has got limitation, because COVID-24 may come, economics may change, politics may change, war may come, and other. We don't know it, but I think something is better than nothing, and it helps in the decision-making process that we need to anticipate what could be some future replacement cost, operational cost, maintenance cost, etc. And so we need to convert all these costs to present value. And there is a formula. So this is a formula that can help us calculate this present value. And once we have determined the present value, we can then calculate life cycle cost, payback period, benefit cost ratios. These are some common economic indicators used in triple bottom line analysis. Now, I'm going to, so as I mentioned to you, that integrated sustainability framework, integrated means that we are integrating 3 tools: environmental life cycle assessment, social life cycle assessment, life cycle costing. These tools by integrating social, economic, environmental indicators, which are determined by using these tools. So that's why it is known as integrating, and we are able to get a single sustainability indicators. It has got number of steps, a good number of equations. What happened that all we have got social indicators, some social indicators, some economic indicators, some environmental indicators. We integrate all social indicators into one indicator, then all economic indicators into one indicator, all environmental indicators into one. So then we have got 3 indicators, one for economic, one for social, one for environmental. Then finally, we integrate all these 3 indicators into one sustainability score. So I give you an example. This is for building industries. One of my students who completed PhD long time ago. I think this is, if you look at here, that is, if you look at this circle, it is comparing the sustainability performance of 5 different types of buildings made of different construction materials, different construction methods, different types of strategies, etc. Now, and if you count, there are at least 22 indicators. Some of them are economic, some of them are social, some of them are environmental, etc. So what happens that there are 5 trends. You'll see that there are 5 trend lines for 5 buildings representing their sustainability performance from these 22 sustainability indicators or triple bottom line indicators. Now, this periphery means that this is the best value. This is the best value. And the indicator that is far away from the periphery represents that it is not doing a good job. In this case, it is the hottest spot, means the gap is very high. So in that case, what we do, when this is the, in that case, we revisit whether it is economic indicator causing having the largest gap, then we do go back to the life cycle costing, which item is in fact causing the increasing the cost. If it is social indicators, then we go back to the social life cycle assessment analysis of that particular product to see which is actually causing the problem. Now, which is actually which variable, which process, which stage actually causing the problem. So same for environmental. So we find out the reason. Once we have found out the reason, then we apply improvement strategies. So we select improvement strategies in a way that it is not, it is actually enhancing all aspects, social aspect, environmental aspect, economic aspects. Now, if you look at this, my cursor, I think, if you look at here, I don't know if you, so this diagram, the diagram on the top is a colorful diagram. The inside circle is blue. It represents existing scenario, and the orange one represents sustainable scenario. So there is a gap between blue zone and orange zone. So and you will find there are 12 buildings, and we have calculated the single score for each building, sustainability score. So means that we have integrated social, economic, and environmental values into one single sustainability score for each of these 12 buildings. And what happened that once we have identified the hottest spot, we implemented improvement strategies. Once we have implemented improvement strategies, we were able to further reduce the gap. So this green zone represents a green building, but nothing is 100% efficient. You cannot 100% close the circular gap. It's like second law of thermodynamics. But something is better than nothing. So more we are able to close the gap, more we are achieving sustainability. That's the thing. Now, why take a LCA approach in decision making? Because I have got lots of personal good experiences, but one of the experience that is relevant to this workshop is I did this project about 13 years ago, collaborated with my colleagues at the University of Western Australia and a government department, Department of Agriculture, Food and Agriculture. So, and University of Western Australia, they provided me with data and I collaborated with the soil scientists. They provided me with fertilizer data, pesticide data, diesel data, farm machinery data, soil emission data, direct soil emission, indirect soil emission, so that I can do the life cycle assessment of biodiesel production from canola seeds. Now, when I uh, uh, determine the functional unit, I have chosen gigajoule, not cubic meter or not kilogram. Why? Because the purpose of the biodiesel is to produce energy, gives us service. So for the same amount of energy, we get different amount of biofuel. So the amount of biofuel that is giving the energy is different to the amount of diesel that is giving the same energy. That's why we have chosen megajoule or gigajoule as a functional unit. And that help us determine the inputs and outputs of used in different stages of product life cycle. Then we converted them to emissions. So, and this is this LCA is a limited focused LCA because we did not estimate other environmental impacts. We only focused on greenhouse gas emission because that this time Australian government introduced carbon trading scheme so that the funder that is Grain Research Development Corporation wanted us to estimate the GHG emission. So there are two significant messages that I will tell you coming up from this analysis, that when we initially use the local IPCC value for soil emission, because it is very expensive and time expensive and resource expensive to measure nitrous oxide from soil. So that's why we initially used IPCC default value. When we use IPCC default value, we found that nitrous oxide emission from paddock or field is the hottest spot. But then we got some grant equivalent to 1 million Australian dollar to appoint research fellow to measure, to stay in the field, to stay in the workstation, to work with the gas chromatograph and gas chambers to measure the amount of nitrous oxide hourly basis. And after 1 year, they gave me one value. So, and that cost a couple of $100,000. So that value, once I have used that local value, that is nitrous oxide, when I saw the local value, it is 50 times less than the IPCC value. And ladies and gentlemen, one thing, this nitrous oxide is 265 times more powerful than normal carbon dioxide emission. So any change in the value of nitrous oxide can make a big change in the total life cycle greenhouse gas emission. So we need to be making sure that we measure this value correctly. You are using the local value. So if it is a biological system, if it is coming from plant, we need to be using the local value. Otherwise, we are underestimating or overestimating the result. But the car, one car, the same car you can produce in Australia and India, not a problem. But you will have different yield of crops on soil in these two countries. So because the quality, climate, everything varies across region. That's the thing. Now, once we have incorporated this local value, it is not the nitrous oxide, but it is the production of fertilizer that is the culprit. We've got the real culprit. So, and it helps in the decision making. Why? Because in the next year, we got another $1 million grant, which was continued for 3 years. So we grew lupin before canola. Lupin can fix nitrogen because it is leguminous crop, and that nitrogen was transferred to canola in the next year, so that the amount of fertilizer application was reduced. Since the amount of fertilizer application was reduced, greenhouse gas emission was reduced. So this is an action research, and that's why LCA is a very powerful tool, a decision-making tool that we have proved. So this graph shows that the production, if we're only considering the production, the biodiesel, if we're using 100%, but there are some technical engine combustion characteristics, it may not allow us to go up to 100 level. We need to sacrifice the performance of the engine. And the production stage, diesel performs better than biofuel because biofuel requires pesticide, herbicide, that is fertilizer, diesel, all these things. So it is an input intensive fuel. But when we are going for combustion, when you burn biodiesel, it produces carbon dioxide, of course, but that carbon dioxide is considered as a biogenic, means it is sequestered by plant. So any carbon dioxide that is emitted due to combustion of biodiesel is considered zero. So that's why in the combustion stage, BD 100 means 100% biodiesel performs better than BD 20, because in BD 20 there are only 20% of biodiesel, 80% diesel. So this is mainly coming from diesel. And so if we're considering the total life cycle emission, so biodiesel performs better than diesel. So that's the message. Now, in the case of social life cycle assessment, this was done, one of my good colleagues at the University of Queensland. I think Manik was his PhD student, and they did the social life cycle assessment of palm oil in Indonesia. So there are main 5 social impact categories. And this graph gives us a very useful message, because the indicator that is far away from the periphery is the hottest spot, and improvement is required. So cultural heritage has been found to be a social hotspot, the number 1 social hotspot, because there was displacement of 2 tribal communities, Orang, Rimba, and Batin. So what could have been some improvement strategies? The government needs to take the measure to fully recognize and protect the rights of the tribal communities who are disadvantaged by the expansion of palm oil plantation. So this is the improvement strategies. And the second second hotspot is working condition. You see the gap is quite high or big. I think this is because of poor working condition, poor wages, etc. So these are some of the social improvement strategies that can be incorporated in order to improve social performance. So what message, what the message is given by this graph are that it can enable us to find out where are some social hotspots, and that can help in the decision-making strategies to come up with some social improvement strategies, etc. Now, there are some like eco-efficiency framework is used. Why this eco-efficiency framework used? Because sometimes when we're improving the environmental performance, nothing is free of cost. So when you are improving the environmental performance, you're putting money. So it is environmentally feasible, but not economically viable. On the other hand, if it is cheap, it is economically feasible, but not environmentally friendly. But there is a framework consisting of a large number of equations, which have not incorporated here, uh, that can help balance both economic and environmental pillars of sustainability. So that's why I have put this figure seesaw effect. So it helps find out which option is the best environmentally friendly option, not entailing the excessive cost. So there's some portfolio position. You see, when you're comparing different products, different fuels, like hydrogen fuel or biofuel or, electric vehicle, okay, uh, that is autonomous technologies. If we're considering different types of transport, we can use this framework because this framework mainly applicable for comparative analysis. Any change in the variable of one product will change the position of another product. So that is what is happening. You see, that is what is happening. Now, so any if this position known as portfolio position, if the portfolio position is on either on or above the diagonal line, is known as coefficient option. Okay, so this is a very smart, intelligent, and useful decision making tool. And for example, we have I think these are, I have given this because this how we can convert different emissions to one single score, which is sustainability score or environmental score, which is known as eco point. So you need to classify, yes, then you need to characterize, because different number of emission gases are causing some impact. You need to convert all these gases under same impact to common impact, which represent this gas like carbon dioxide for global warming. So once you have converted to equivalent amount of impact, you need to compare with the national average. You can get rid of units, so you can normalize. Then you need to multiply it by the corresponding weight, because different environmental impacts have different weights. So this is how you can compare, you can convert large number of emissions to one single score, which is known as eco unit. So this is used when we use this framework, because we need to convert all environmental impacts to one single unit. Now, in this means this is the one, and so each option, there are 6 options. Uh, uh, we have considered different options, like we reduce the load restriction, because engine the lowest limit was 30%. So, but engine was unnecessarily running, so we reduced it to 10%. And then we have considered, yes, the exhaust gas can be used as supercharger. Also considered that, yes, we can use some energy. So this is Coral Reef. One of my doctoral students completed a couple of years ago, that a Coral Reef, Coral Bay in Western Australia, full of wind. So I think most of the energy comes from wind. So remaining comes from diesel. So in order to make it more eco-efficient, we have considered all these technological improvement strategies, also considered the use of rooftop panel of different sizes. So we found that these eco-efficient options, that these are the 3 options, they are both economically and environmentally friendly. So eco-efficiency framework enable us to come to a decision that what to do, which option to choose, etc. Now, the reason I'm discussing this difference between weak sustainability and strong sustainability, because I think The reason, because I developed a framework for my another PhD student that that framework should follow a strong sustainability. If you look at this nested diagram, that determines the strong sustainability, because we have got one earth. We need to cut our cloth according to the code. We cannot exceed the biophysical limit. We cannot exceed the carrying capacity. So our technological design or our economic development, social development needs to take into account the biophysical limitation or carrying capacity or biophysical limit of Mother Nature. So that framework, according to the framework, it is for biofuel, different types of transportation fuel. Like, so first they have to meet environmental criteria. There are some threshold value, means they have to achieve this threshold value. If not, they cannot go for social assessment. We need to apply improvement strategies until and unless it becomes environmentally friendly. Once that option becomes environmentally friendly, then we go for social assessment. Once it is socially viable, then we can go for economic assessment. So we have published about 5 papers in good journal. Now, so what happened that we have considered these 4 types of transportation system using hydrogen, if 65. The reason we have considered 65 because this is the optimum engine combustion performance and fuel efficiency it can give. Electric vehicle, plug-in hybrid electric vehicle using both electricity and petrol. So we have considered these 4. We selected these 4 indicators on the basis of the expert survey that I mentioned to you. Unfortunately, none of them found completely environmentally sustainable. So in the case of social performance, there are 4 indicators that we also selected by interviewing people, expert, local job creation, conservation of fossil fuel for future generation, which is intergenerational social equity, occupational health and safety, reduction in household expenditure by switching to different fuel. And in this case, we found that it is better than environmental aspects. So some fuels, they met the environmental target. Social. Most of the fuel options met the social sustainability target. But in the case of economic indicators, we had 2 variables, 2 indicators: net benefit, carbon reduction credit. Most of them did not meet the criteria. So we know where is the problem. Now we investigated into life cycle costing, social life cycle assessment, environmental life cycle assessment. We went back to the inventory. We tried to see which item is actually increasing the cost, which where is the main social problem, where is the main environmental problem, where improvement is needed, and in order to improve them, what technological improvement is needed. So accordingly, we have selected technologies. So for hydrogen, we have considered these options like renewable electricity for hydrogen production, utilization of oxygen byproduct. We consider all possible ways. So why this framework is important, help us determine the sustainability strategies or improvement strategies that helps what could be the right strategies or what solution to achieve the sustainable development. So we have considered these strategies for hydrogen, all these strategies for electric vehicle. So, and then we try to see whether all environmental, social, and economic criteria have met the threshold value. The case of hydrogen, it was not sustainable because economic. It is sustainable from social and environmental, but not from economical aspect. But in the case of electric vehicle, after incorporating these strategies, we found that yes, they met all the criteria, so they are sustainable. In the case of plug-in hybrid vehicle, we have to consider the use of all these technological options. Then after considering all these improvement strategies, we found that yes, all economic, social, and environmental criteria met, and it uh, it actually that achieve sustainability. So same for E65. What is the message? That this is a framework that enable us to find out where is the problem, what could be some right technological solution that will enable meet environmental, social, and economic criteria, sustainable criteria to become sustainable fuel. And this framework can potentially be utilized by the government or ministry to decide which fuel to use, what strategies to be implemented, and it will vary from country to country, region to region, etc. Now, my last slide at life cycle assessment is a decision support tool. It can help which option to consider, which fuel to consider, what improvement strategies needs to be taken, what is the right strategy, should there be economic, social, or environmental improvement. It is a diagnostic tool, like it is a diagnostic tool for engineers because it helps engineers to find out where is the problem so that appropriate right technological solution is a prescription like a medicine. Engineers can prescribe medicine. So selection of improvement strategies, further sustainable development by identifying the hotspot, incorporating improvement strategies to further reducing the gap, and selection of the most sustainable option. So thank you very much. Sorry for taking extra time, and thanks for giving me this opportunity.
So thanks a lot, sir, for your valuable information and discussion on the integrated sustainability framework. So we have quick questions in the chat box from the participants. Sir, the question is from Uma Durgesh. Is asking us to advise the integrated LCA and scoring tool is available for general use.
Okay, so I go to the first question. Okay, that is, can you kindly advise examples of latest innovation in which one? This is which the first question?
Yes, sir. It's like the same person, sir, Uma Durgesh. Can you advise examples of latest innovations for electronic waste recycling technologies? Is first question. And second question is, can you advise the integrated LCA and scoring tool available for general use? The third question, sir. So two questions from Uma Durgesh.
Okay, thank you. So electric waste recycling technologies, electronic waste, I think this is a challenging aspect. I think, of course, people are recovering lithium. Lithium is not yet economically viable. Solar panel recycling is very important. Remanufacturing is important, but it's still not viable. People are only using the glasses. But we will be running out of silicon rock by 2050 when people will be switching to clean energy in order to meet the net zero emission target. So I think recycling is a challenging. I think it's still a very challenging area, and we are running out of rare earth material. I think there are, and sometimes recycling is so expensive. People find it is good to buy new product rather than recycling. Now, if you are coming to that. So this integrated framework can be used for anything. You can use it for building construction, building material selection, building sustainability assessment, that is manufacturing sustainability assessment, energy sustainability assessment, transportation sustainability assessment. This can be used. This is a framework. This is a tool that can be used. Yes, that can be used for anything. It can be used to assess human beings as well, not a problem, because this is a framework. So different people have different consumption pattern, different ecological footprint, different type of emission. My carbon footprint will be different to your carbon footprint. So it can be used for anything else. And can you advise integrated LCA scoring tool available for general use? Yes, of course, because this can be used for you can use for anything, assessing the sustainability of anything. It's not an issue. So, and can you please discuss brief about social life cycle assessment, like input parameters? The social life cycle assessment, those are the people, stakeholders, like labor, manufacturer, manager, then community, those who are affected by the production process, and pressure group. They are the stakeholders, so who are directly owned, and you need to ask them. So different indicators, social indicators, they are relevant to different indicators. So, and the different stakeholders who are directly or indirectly affected by the production of a product can give you some feedback, qualitative feedback, their satisfaction, dissatisfaction, partial satisfaction, etc. And this integrated sustainability assessment framework can help you convert this qualitative value to quantitative value. I have already discussed this with you. Then carbon emission from 100% biodiesel production is shown as zero. This is a biogenic in the combustion, because when you burn any CO2 that is burned from plant-based material, because biodiesel is produced from canola, which is a plant-based material, that is known as biogenic. And biogenic means the value of carbon dioxide value is zero. So I cannot go further because I'm not an atmospheric scientist. Those are atmospheric scientists, they have considered this as a zero, because somehow it comes from plant, it will be somehow be sequestered by plant. That's the thing. Now, that is, I request your clarification if carbon dioxide from biogenic source should be considered. Yes, of course, that we published in Impact Factor 9 journal, Environmental Science and Technology. And also, as you mentioned about the second law of thermodynamics, please share your opinion on the concept of sustainability. Second law of thermodynamics means nothing is perfect in this world, means that you cannot achieve 100%. It is difficult to achieve anything 100%, because there will be some system laws. You cannot make renewable energy technologies without non-renewable energy technologies, okay? The aluminum glass that you are using or silicon rock you're using are non-renewable. So one of the things we can do, we can reduce the population size of the population. That is the main thing to do. Reduce the consumption, reduce the production, and maximize the resource efficiency. That are something. But I think SDG is a goal, but mainly that it has got a sustainable development goal. It has got some issue. By issue, it is mainly relevant to developing countries, but it doesn't completely reflect the economic situation of developed nations. Different to different countries. Some, because I think there is an issue, I think, with SDG. So these are my responses. So am I clear? Please let me know if I am clear. So if you need further clarification, please put up your hand. I'm happy to clarify further.
So I don't see anyone. So I think thank you. Yeah, some people are putting thank you very much. So that's good. So thank you, Dr. Biswas, Professor Biswas, for the wonderful talk. And we will again, we will have similar workshops in future. So we will look forward to hearing you more on different aspects of the sustainability and the work that you have been doing. So really nice to see your face. We have exchanged emails, we have exchanged phone calls, but never had a chance to meet. Maybe one day we'll meet also physically.
Of course. There will be an opportunity. And thanks for giving me this opportunity. And thanks for taking a bit extra time. Thank you very much,
Okay.
Professor
Thank you.
Dubey. Much appreciated. And I feel honored. Thank you very much
Okay.
indeed.
Thank you, Dada. Thank you. Bye.
Thank you very much. Good.